For the second part of my lecture today, I will try to talk about a more workable definition of privacy. And actually, sorry, not more workable definition of privacy. That Kobe will talk about that next. About about a more meaningful notion of a privacy breach, like what it means to breach privacy, which hopefully will provide motivation for a more robust notion of what privacy is. Like I said, I'm not a theoretician, other lecturers, they use these Greek symbols. I don't speak Greek, don't know. So I'm motivated by real world uses of data. And as I already mentioned, an interesting trend that's going on is commoditizing machine learning, okay? And providing machine learning as a service. And the reason it's interesting to me as a security researcher is that, wow, that's pretty cool. That's Second Amendment equivalent of machine learning, which is what if we give everybody access to a machine gun? Let's see what we can get away with here. And that's kind of what's happening is because there is huge demand for machine learning. There are lots of people with data sets, big data sets, small data sets. They want to make use of their data sets. They've heard of this machine learning thing. They want to apply it, but it's kind of hard to hire a machine learning expert. It's hard to learn to understand machine learning. And so these companies like Google and Amazon and Microsoft that are good at learning, they're now providing it as a service. And you too, madam, could be a machine learning expert. Just come and upload your data and use the service. And that has very interesting implications because I have full reason to believe that people are going to be using it for purposes and in ways that designers of these services didn't intend at all. So here is how the services work. They provide something called training API. And by the way, it's actually just to be clear, these services exist not just to out of goodness of Google's heart, so to speak. They exist, both it's a paid service, so they make money, but also they it's an incentive for people to upload data into Amazon Cloud or Google Cloud. So this is to make their services a little stickier so that people use their cloud storage services more. So anyhow, so they provide something called training API that anybody can use. It's not, you can play with it yourself for a few bucks. And if I am a data holder, I collected some data from someone, maybe I have an app, okay, of some kind, and that app interacts with users. I have a game, I don't know, I want to figure out how to better upsell my users on in-app purchases so that they, it's a game, Dungeons and Dragons, and I want to be selling potions in that game for real money, how to market that better. You guys are laughing. That's $1 billion business, right there. So, so I take my data, I upload it to this training API, and then I push a button, and hamsters run in a wheel in Mountain View somewhere, and they produce a model, okay? And you might ask, wait, what model are we talking? What are we talking about? Neural network, SVM, random forest? Well, interestingly enough, in part because it's actually a paid business for Google, they don't tell you what the model is. They don't even tell you what algorithm, even the type of the model they don't tell you. Did they use logistic regression? Did they train a perceptron? They don't tell you what the model is because, don't worry your pretty head about that. And instead, they give you another API, so-called prediction API, that effectively gives you black box access to that model. So you can give an input to that prediction API, and boom, out comes an output. Typically, like I said, these are classification models. So out comes a classification, and you can access it and so on. And this data could be sensitive. As always, it could be transactions, preferences of people, online, offline behavior, who knows what goes in that data. And admittedly, most users of this machine learning as a service are targeting internal use, right? So there is no adversary in some sense. It's the person who knows the data is the person who is working with the model. So in that case, there is no privacy issue other than like Google knows everything type of issue. But that's a separate line of research that I'm happy to talk about offline, but not today. You know, how to protect it all from Google. But also, like, it's not the only use, because in many situations, like if we're talking about analyzing like online behavior or in-app purchases or like mobile apps, what have you, the adversary, like a third party, gets to interact at least indirectly with the model. Meaning that, like, if I do, let's think of a game. Okay, I do something with a game, it gives me a certain offer. If that's based on the model of other people's behavior, this means that there is leakage of information. So for the purposes of the rest of this talk, I will assume that an adversary gets to submit queries to prediction API and get outputs. It's not always the case, but it happens often enough that that's a realistic model. So now what we have here sensitive data. We have a black box model trained on that data, and we have an adversary who can submit an input and get an output, submit an input and get an output. And the general question I'm going to ask is this: can an adversary, by interacting with a black box model, learn something about the data on which it was trained? Okay? That's not the model inversion question. So I'm not asking, like, can I learn from the output about the input? In this case, the adversary is providing the input and is observing the output. So there is nothing to learn about the input. The adversary has the input. It's purely a question about privacy of the training data. Okay? So my goal as an adversary would be, I submit an input, get an output, submit an input, get an output, do it a bunch of times, and then I will try to figure out what was in the training data on which the model was trained. Okay? Does that problem setting make sense? Yeah? Okay. So how might I go about something like this? And by the way, this problem, okay, sorry, just bear with me. So how might I go something like this? Well, it turns out, and this is just an empirical observation. This is something that we noticed, or rather, all of this work was done with a postdoc of mine by the name of Reza Shokri, so that's what Reza noticed. So what he noticed is this. So if you give the model an input that was actually part of its training data set, it gives you certain classification, and as I described an hour ago, a classification is a vector of probabilities. It gives you a certain vector of probabilities. And if you give it an input that's not part of its training data set, it gives you also, of course, a vector. It always gives you a vector of probabilities. And somehow these vectors look different. Okay, in what sense different? Well, like first order signal, it's often a little more confident on its predictions for inputs from its training set. Okay, it has seen those things before. It's a little more confident. But it's not as simple as that. Actually, like, the strongest signal is not the strength of its confidence. It misclassifies things in a different way. Like its second best guess and third best guess, they seem to differ like in various ways between when it's given an input from its training data set and input not from its training data set. Of course, like, if you're a machine learning person, like, your immediate reaction should be like, okay, if there are like some differences, like this means the model is not regularized well, I'll come back to that. I promise you, I'll talk to you at length, like why this is happening. But for now, let's just work with something simple here, which is, so we have a difference here, right? We have a difference, but it's very difficult to capture like analytically. It's very difficult to write a formula that kind of captures like what is the difference between its behavior on inputs from its training data set and not. So we struggled with this for a while until we had like a good idea, okay? And the good idea was like, as always, like a dumb idea, which is like the simplest thing possible, which is, okay, look, we don't know ourselves how to tell the difference between the model's behavior on inputs it has seen before and its behavior on inputs it hasn't seen. So it's hard for a human, but you know what? We've heard of this amazing technology called machine learning that is claimed to outperform humans. Why don't we use that, okay, to make it even better, why don't we use the very same like black box like Google API to learn how to distinguish the behavior of models trained on Google API? Okay, so that's kind of turning machine learning against itself and teaching machine learning to extract information from machine learning models. So why don't we, in order to recognize this difference, why don't we train a model to do this? All right, so that sounds, kind of one of these like, that is like awesome, okay, if I say so myself, again. But in reality, like doing this, like kind of, it's an interesting intuition that you can use machine learning to solve problems where you cannot solve like explicitly and analytically. But if you were to try to do this, pretty soon you run into obstacles, okay? And there is one obstacle here like right away that should be immediately obvious. And what do you think that obstacle is? Let me see, is that on my slides? I hope it's not, because otherwise it's like, I hate this when like you give a test and like everybody knows the answer. It's not cool, but no, it's not on the slides. So what do you think is like the hardest challenge in applying this idea? So just to reiterate, so we have a suspicion that models trained on this machine learning as a platform, machine learning as a service platform, they behave differently on inputs from its training data set or not. But how, and we want to train a model to recognize the difference, yeah. What's our training set? Like how do we generate training? Because to do this, we need training data, but if we're attacking a model, like, what do we use as the training data? Okay, yes, that's a problem, indeed. And of course, we could assume that maybe the adversary knows a lot about the data on which the model was trained in the first place. Like maybe he knows the distribution of the training data, and then he can sample from the same distribution, and so on. So while you're thinking about this problem, so I'll tell you about the technique that we use to train the attack model, then I'll tell you where the training data comes from. So it turns out, and this is kind of very empirical. There is no rigorous scientific basis for why this should work, but empirically it works pretty well. Reza invented this technique called shadow training. And this is designed to deal with this problem of how do you learn to understand the behavior of a black box model where you don't know the specifics of the model. So this slide is going to take me a while to work through because there is a lot going on here. So here is the intuition behind what we're trying to do. The problem with training, okay, so let me come back to this picture. So we want to train a model to recognize the difference. Yeah. Mm.
What's the problem just to, you get a set of vectors which you know are from the original training.
Right, but how do you know they're from the original training data set? Like if you knew they're from, what?
You assume you're the one created it.
Well, I mean, there are three parties here. There is the person who has the data, and there is the Google who created the model, and then there is us, the adversary. So our goal is to reconstruct the data, so we don't know. What? I give my own inputs, and I get the outputs from the model, but I don't, that database on the right, my goal is to reconstruct that.
That's only because you want to specifically attack Google servers. If you could set up your own servers, do the whole thing to train the model, and then run it on something else.
Well, I mean, what I want to attack is the model trained by Google on somebody else's data.
Specifically there, it's not a general feasibility of doing.
It's not a general feasibility of anything, but the technique I give you is not specific to Google because the technique is black box. It doesn't matter what's in the black box of the model. Okay, so to train something like this, so I need lots of examples. Okay, and these examples they have to be examples of behavior of the model on inputs from its training data set and behavior of the model on inputs not from its training data set. So I need like sort of lots of positive examples and lots of negative examples. That's what would allow me to train this attack model. So where might those come from? So that's the idea of shadow training. So let me come back here. So the idea is this. So I have this target model. I am going to create a bunch of clones. I mean, they're not going to be exactly clones, but they're going to be something like my local models that I hope behave like the target model. So I can even train them using the same service, but I'm going to train them on my own data. The reason I want these shadow models is that for the shadow models, I actually know the ground truth. So because I completely control the training data set for each shadow model, I know which things are in the training data set and not in the training data set. So, which means that I can train my own shadow models, a whole bunch of them. I mean, I guess I could get away with just one, but for reasons that I don't actually fully understand, it works much better if I have multiple models. And for each one of them, I have a bunch of examples that are in the training data set, a bunch of examples that are not in the training data set. And I can submit them to the shadow model and I get the output, which means that now I have a whole bunch of pairs, like in the training data set, this is what the shadow model produced. Not in the training data set. This is what the shadow model produced. In the training data set, output of the shadow model. Not in the training data set, output of the shadow model. Okay? And once I have a bunch of these examples, I can train basically a binary classifier at this point, which takes an input, takes the output of the shadow model, and I tell it, okay, that's the truth. It was in, it was out. Okay, so now I can do supervised training, and I can try to train a classifier that by looking at an input and the output of the shadow model predicts accurately if that input was in the training data set or not. So that is trained on the shadow models, but then I will apply it to the target model and hope, and I'll explain why my hope is justified, I hope that it'll work as well on the target model as it worked on my shadow models. Now, it's a pretty complex process, so it's like, yeah.
Isn't there some hidden assumption that one of your shadow models thinks that is similar to...
Yeah, absolutely, absolutely. I mean, like, nothing here would work if shadow models didn't behave in a way that's similar to the target model. All I can tell you about that assumption is that empirically, experimentally, it works for us. There are no theorems here, okay? That's coming like after lunch, okay? There are no like formal statements of any kind. Like as I opened this morning, these are tales from the like rough streets of New York, okay? That's just what we do. These are like all empirical results. But hold that thought because yeah. Okay, good point. So, okay, no, okay. So we assume nothing, okay, because we don't know what it is, except that we know the service which constructed it, okay? So here is why, like, our shadow models, we believe, are going to be similar to the target model, okay? If we can find training data that is similar, for some vague notion of similarity, to the target model's training data, and construct a model using the same service as was used to construct the target model, we hope that it's going to give us a shadow model that's similar to the target model. Okay?
And if you say you have experimental evidence that there's theory behind that, how many different models did you then test usually?
We have like a whole paper about this, okay? Like when it worked, when it didn't work, why we think it didn't work, and so on. So just bear with me, okay? Let me describe the whole process, then I'll answer those questions. Okay, but that is the critical question. So that's exactly where like the action is because everything here would work provided like the effective assumption here is that our training data for shadow models is similar to the training data for target model. It's trained through the same process. Therefore, when we learn to distinguish on shadow models, the distinguisher is going to work well on the target model, okay? But that's really the hardest part. It's like training data for the shadow models. How do we do this? Okay, so we have several ways of doing this, okay? So one way is, I mean, we sort of played with different ways. Maybe we know the distribution of data, like from which distribution the data for the target model was drawn. Then we just sample from the same distribution, okay? Another way is that we played with like various purchase data sets and kind of retail type thing, where maybe we know like, you know, it's a vector of features, and for each feature we know marginal distribution, right? We know like, you know, the distribution of each element, and we create synthetic records by sampling from those marginal distributions. And you can even do better, like if you know joint distributions, you can sample from joint distributions. That does really assume quite a bit of knowledge about the training data set of the target model. Like knowing like marginal distributions of values, it's almost like, you know, it still has value from the privacy perspective, because maybe you know the distribution, but you don't know the exact samples that they used for training, and actually the privacy isn't the exact samples that they used. But it does assume some knowledge. So we did a bunch of experiments with this one, with that one, but here is another one which I find cute, which is another form of like synthetic generation of training data, where we use the target model itself to extract training data for the shadow models. So we're sort of hoping maybe the target model will tell us which data to use to train our shadows. So here is, let me give you an intuition for how this process works. So let's say this is like the whole like input space, and that thing on the left is training inputs of the target. If you look, and I mean, this is all like, it's not a formal statement, it's just like an intuition. If you look at the confidence of target models' prediction, they tend to be higher on things it has seen before, okay? That's just an empirical fact, which means that if we just explore the space of inputs and sort of sample synthetic training data for our shadows from the space where the target model gives confident predictions, our training data is going to be similar and maybe even overlapping with the training data of the target. So that's the intuition, is to create training data for our shadows from inputs that are classified with target model with high confidence. Yeah?
So in this case, you're just gonna like look at the confidence, and if this confidence is high, I'm gonna train my shadow model assuming that this example is the training set? Because
No. Okay. Because all that'll teach us to do is to recognize things that have high confidence. No. Something much more subtle is going on here, okay? So let me go back, okay? Sorry. And I'm gonna get off the stage. So this part is very important. All inputs here, in and out, are classified by the target model with high confidence. We're going to use only some of them to train the shadow model. And so we're going to train our distinguisher given an input. Some of them are in and some of them are out, even though all of them are classified with high confidence by the target model. So we're going to teach our distinguisher to distinguish between high confidence inputs that are in and high confidence inputs that are out. And that's why what we're learning here is not just to recognize things that the target model classifies with high confidence. We're teaching like this classifier on shadows to like recognize much subtler distinctions. That does make some kind of intuitive sense. Like Adam looks totally like, God, what is he ranting about? But so it's, no, that's an excellent question. And that's a very understandable confusion. So something much more subtle is going on here. So both of these tests are sampled from the high confidence space of the target model. And then we cut them into training and test and learn to, and teach this classifier to distinguish between what's in and what's out, okay? And because of this, yeah?
But how do you, I mean, you give the service examples, just like random examples, and then you see what's on the
We don't give random, no, like, okay, so we do this process, okay? We draw from this space and we get like a big synthetic data set. Then on half of that synthetic data set, we train a whole bunch of shadow models, okay? Then we run those shadow models on their training data and on something that wasn't on their training data. That gives us a whole lot of examples. Input, output of the shadow model, input, output of the shadow model, and for each one we know if it was in the training data set or not, okay? And on that data, we train a binary classifier, which is our actual attack model. And what the binary classifier, it takes in an input, it takes in the output of a shadow model, and it learns to respond with high confidence if that input was in the training data set or not, okay? And then we apply that to the target model. That's the process, okay? It's lots of things going on here. Yeah? I'm sorry, it's very hard to hear. I'm sorry, the classifier is not learning to...
I was wondering, like, could you do some kind of search, like to add, you find some data that you know, you think was the training that the target model was trained with, then you add some noise and then you check like how close does this look to.
Okay, we could. Okay, let me postpone this question until the end, okay? I mean, we tried many things to get it to work, but just to make one thing clear, sorry, I have to go back here. Like, this picture is important, is that the attack model is not trained on the target model at all. It's trained on these shadows. All we use the target model for is to generate a space of inputs that are classified by the target model with high confidence, okay? All the training of the attack model is done on shadows where we control everything. We know what's in, we know what's out, we know the ground truth, we can label everything. So, right. Okay, so that's, yeah. So that's kind of the algorithm for synthesizing shadow training data, and it works kind of in a kind of predictable way. So here there is some very simple hill climbing of space of possible inputs to find those classified by the target model with high confidence. And let me tell you right away. So this only works if somehow the space of inputs classified with high confidence by the target model is like very structured and like easy to explore. I can easily imagine models where just discovering inputs that are classified with high confidence by the target model is in itself like a hard problem, and like this method of generating data would not work. The only way you would do this is like you'd be able to do this if you have some a priori knowledge of the distribution from which the training inputs for the target were drawn. So I admit right away that this only works if there is actually this step is actually feasible. And then you sample from these inputs to synthesize the training data set for shadow models, and if it turns out that you're in some part of the space where like many candidate inputs are rejected, you re-randomize a bunch of features and try again. And there is absolutely no guarantee that this process actually yields like enough training data to train anything. It's all like very empirical. Does work pretty well on the models we've played with. Okay, and once we do this, this gives rise to a very basic attack, okay? Which nevertheless, I will claim, unlike model inversion, is a real privacy attack, and I'll call it membership inference. So our goal, the goal of this attack is to learn one bit of information, okay? Like this. I get an image, well, it doesn't have to be an image, but I get an input into the model. I put it through my target model, which is black box. I don't know its structure, I don't know what it's doing. Might not even be a neural network. I get a vector of confidences. And then by looking at this vector of confidence, my attack model gives me one bit of information. Was this image part of the training data set or not? So that's what I'll call a membership inference oracle. Given an input and given access to a model, it predicts, predict is not the right word. It infers whether that input was part of the training set for that model. And when applied to this machine learning as a service, it works like this. So you have a certain target data record, and then you put it through the model, and by looking at the output of the prediction API, you can tell if this record was on the training data set of this model or not. It actually works pretty well. Interestingly enough, it doesn't work well on all classes, okay? So in a multi-class model, we often see like for some classes it works well, and for some classes it doesn't work well. But you know, on some natural classification tasks, we can get to like, for 75% of classes, we could get to like 90% accuracy. Let me just mention briefly one thing, and then I'm going to spend some time talking about like why this thing even works and like what conclusions we should draw from this and so on. You might think that one simple way to defeat this attack is to give not as fine-grained an output of the model, because what our attack model is working on, it assumes that we have full confidence vector of the model, meaning that we have a probability for every possible class, which is really a lot of information. So here are obvious ways you would defeat this. Don't output probabilities for all classes, output it for top k. Okay, that's a reasonable thing. Output probabilities at finer granularity, or here is one. Don't output probabilities at all, just output top k classes. Here is an interesting fact. Our attack still works, not as accurately, but still works pretty well, even if it has no probabilities. Well, how could it work without having any numbers? What is the signal? Misclassifications is the signal. So it turns out that like inputs from the training data set, not from the training data set, when they're misclassified as different classes. Which means that even if you're just outputting like classes, no probabilities at all, just like top k classes, there is still signal there and still like discrepancies in behavior on inputs in the training data set or not that provide some signal for our attack model to work. So kind of obvious mitigations don't work. The only thing that would work is actually like differential privacy. But okay. All right, so let's see here. So you could actually leverage this attack into a little more. So far it's just a membership inference oracle, but you can imagine, what if I don't have a complete record? What if I have a partial record? Well, if you have a partial record, at least in theory, you could use this attack to complete the parts you don't know. Like, the most brute force way you can think about it is do what? Like, give me the most like brute force way to turn like membership inference attack into a reconstruction attack. What? Don't be shy. Just try like all options and see which one tells you, yes, that was in the training data set. It actually, that's the obvious idea. It's actually harder to do than it seems, because it turns out that once you get like real close to the right record, sometimes, you know, you start getting mistakes there. It's like your oracle tells you like yes, even though it's not. But you can infer hidden parts there, but you can do smarter things. So there is a lot you can do there. Now let's talk about why these attacks work. Okay, why is this even happening? Why, you know, can I train a machine, my own machine learning model to tell the difference in the target model's behavior on inputs from and out training data set? Well, like first order explanation is, and maybe the only explanation is, the target model is overfitted. Okay, what do I want to say about this? So, two things. So first of all, it's not like the complete explanation. If you take a standard metric of overfitting, which would be something like test train gap, we often see, like we would see a model on Amazon and a model on Google for the same task that have the same test train gap, and yet our membership inference attacks work much better against one than against the other. I actually don't quite know why that's the case, but because we don't like structurally know what the models are, but it does seem like at least the way we implemented the attack or the way we did it, like test train gap by itself does not tell us like right away like how successful our attack is going to be. So there is clearly a connection to overfitting, but it's not like perfect. Also, avoiding overfitting in this setting is actually very hard because like how would you avoid overfitting? Like whose responsibility is it even to avoid overfitting? I mean, this is machine learning as a service, which means like any punter on the street can bring their own data set and like train it for an arbitrary task. Like how could you, like avoiding overfitting is like very difficult because they bring the data, maybe they give you this multi-classification problems where some classes don't have enough representatives in the data set. It's hard, you know, for a service to avoid overfitting. What they should be doing though, like what they should really be doing, they should be like warning people about the dangers of overfitting, that you're not only gonna end up with a crappy model, I mean, your model is gonna leak. I mean, they don't do any of that. They give you like very little information there. These charts I kind of like. So what they show you, like this is, so what we have on the x-axis, you probably can't see it, but you can see it on your slide. That's the test train accuracy gap. So that's the standard metric of overfitting. And what we have on the y-axis is attack prediction. I mean, the success of our attack. And you can see they're sort of on a line, right? Which shows you that there is a relationship between overfitting and success of our attack. Like the more overfitted it is, according to standard overfitting metrics, the more successful our attack is. So it basically succeeds like in the area where models are overfitted, modulo that disclaimer that I just gave, which is we do see often models that have the same test train gap and our attack works against one and doesn't work against the other, or like there is a significant gap in accuracy. Don't really know why, but these charts, I like them. I mean, to me, they're very convincing by showing that there is a relationship between overfitting and success of membership inference. Now let me take a broader view of the whole thing, which hopefully will motivate the rest of the day today. Yeah?
The test train graph is a Boolean thing. It's a binary thing, right? You're measuring where you, it's not a matter of what the weight is. You measure whether you classify it as yes or no, irrespective of the weight. Could very well be, though, that the weight on training data is higher, so it's a statistically stronger yes than other values, so it's not reflected in the test train gap, but it does give
that could be. It's so what you're saying is that there could be stronger measures of overfitting, and I would argue, okay, immodestly, that our membership inference attacks could be thought of as like yet another way of measuring overfitting, like sort of as an alternative to test train gap. So I would suggest that, like, you know, if somebody constructs a model, run our attack and see, you know, what it gives you. Like, if it succeeds, maybe it indicates some overfitting.
You can also try to see what the correlation becomes when you look at the test train gap, not as a binary thing,
but adjusted for, yeah. There are lots of things that could be done there. But there are people here who know much more about machine learning and how to measure overfitting than I do, but yeah. Okay, so now let me kind of paint a broader picture here. So, so we have a data universe, you know, we draw some sample from it, we construct a model. So the question I've been asking so far, the privacy question, does the model leak information about data in the training data set? Machine learning people, by and large, they're not worried about privacy all that much. What they care about, among other things, they care about generalizability of their models. They care about predictive power. They want to ask, like, does this model generalize to data outside the training data set? If I took a different sample and applied the model, is it going to have the same predictive power? In some sense, that's what test train gap is measuring. Now, do you guys notice anything about these two questions? What do you notice about them? Yeah. So the first thing is that overfitting is like a common enemy here. That overfitting makes privacy worse, and overfitting prevents the model from generalizing. You could also, I mean, this is not a mathematical statement, but if you squint just so, you could even say, like, maybe this is the same question, okay? Maybe it's really like the same question about, like, the privacy question and the generalizability question is really asking about the same thing, okay? Because certainly membership inference is a question about how much information is leaking about the training data set. And one thing I can tell you for sure, if the model is perfectly generalizable, what can you tell about my attacks, membership inference attacks? They have to fail. Like there is no way, they cannot possibly work against a model that is perfectly generalized. Now, it's not, I mean, a model that outputs a random number everywhere is perfectly generalizable, right? And my attack doesn't work. It's not a useful model, but yeah?
But isn't it the case that if a very model with a particular hack model that is very generalizable, they still do not protect against this reconstructed directives?
Well, yes. It's a very deep question you're asking. So the reconstruction question needs to be asked right. Otherwise, I'm going to end up in the model inversion business again. Okay? This is very important because, like, if I define reconstruction carelessly, I'm just going to define model inversion thing. Like, can I, given the output of the model, can I reconstruct the input? Okay? Which is like, yes, you can. I mean, that's the whole point of the model, is to learn things about the input. I mean, that's like scientific knowledge, and I'm back where I started. So actually, like in our paper, we like do not even attempt to tackle reconstruction. This is something that we're trying to work on, and like I still have to find like the right definition that doesn't get me into model inversion business. But as far as membership inference, which is a very clear like privacy question on a well generalized model, shouldn't work at all. So overfitting is the common enemy. So the good news is that what this tells you is that there's probably like a fruitful like interplay here, which is like machine learning people know from overfitting. I mean, that's what they deal with, like, you know, all day, every day, right? And what this tells me is that the techniques that we use for privacy could be useful to obtain well-generalized model. So that's the whole, like, something that we're going to hear about, like differential privacy as a regularization technique, as a way of not just getting privacy, but getting a good model. But I have a sense that it works the other way, that if you look at all the nice techniques that people have used for regularizing, like dropout and all kinds of like stochastic things, they could be viewed as privacy mechanisms to the extent they prevent overfitting to the training data. Now, I don't know like in what sense, I mean, some of these mechanisms have a differential privacy interpretation, and maybe we'll hear about some of that later today. Okay, if you believe that like differential privacy is like the truth and the only truth and the ultimate truth, then there is no like God other than the differential privacy, and like you have. But if there might be other notions of privacy that somehow emerge from these regularization techniques, but I will not talk about this in this room here. Okay. So, but the big idea here is that there is like a deep connection between privacy and overfitting, and I feel that these membership inference attacks are illustrating it nicely. And they also address this issue that I try to motivate with model inversion, like when does inference breach privacy? So remember our setting here. So we constructed a model from the training data set, and we can infer things. So by definition, membership inference only infers things about members of the training data set. So the privacy breaches done using the techniques I've just described, they correspond to the risk of membership, and you can sort of say that like this gap between what can be inferred about from the model about a member and about an arbitrary input from the population, that's exactly the risk of membership. That's like the extra harm that comes to you if you allow your data to be used to construct a model, which I think is like basically like the original motivation for differential privacy. I don't know. You guys are like sitting in the room, so but that is what?
I mean, that's exactly right. If you try to write down a formalization of what it means to resist membership inference attacks,
You're going to come up with something like differential privacy. So, and that's the difference between like membership inference and model inversion. It's like inferring things about that are true about population, that's like science, okay? And inferring things that are only true about members of the, of course, but you have to be careful, it's like the extra thing. I mean, of course, whatever you can infer about members of the population, you can infer about members of the training data set, okay? just because they're members of the population as well. It's that extra that you infer about members of the training data set, but that you cannot infer about arbitrary members of the population. It's that like little added. So that is exactly the privacy breach, the extra information you learn about someone because their data was used in the training data set, beyond what you learn about them as members of the population just from the fact that you have a model that captures something about the population. So unlike model inversion that goes for the absolute notion of privacy, here we're going for the relative notion of privacy. Here is, okay, so the model tells you something about the population, but it looks like, in addition to that, I can learn something about people just because they're in the training data set. And that extra part, which is represented here by this massive red arrow, very mathematical, that's the privacy breach, okay? And you can see it actually pretty concretely, because when we run our attacks on members of the training data set, and we also tried running them on non-members of the training data set, you see the gap there. And that gap is exactly the risk of membership and what extra we can infer. So whereas what we infer for non-members is very close to the baseline. It's like the reason it's not quite at the baseline is because it's kind of like a naive baseline. It doesn't take like joint distributions into account. If you compute like baseline in a smarter way, what we learn about non-members is exactly the baseline, which is to say what you can learn about them just by knowing statistics of the population, okay? All right, so where does this leave us? So somehow, there is a very nice connection between privacy and learning here. And this is why like, it's exciting. As a privacy researcher, you spend like all your life like sort of bringing bad news to people, okay? You tell them, you know what, you want to release this data set, but you really can't because bad things are going to happen. And they're like, well, what if we generalize it just so? And you're like, well, not really, okay? And there is always this like sort of knob, right? Even with differential privacy in most of its application, it's like, all right, so turn epsilon over here, and then you get like this like super noisy output, or turn it over there, and then the output is more accurate, but you leak more. So there is always this like trade-off between privacy and utility. But here, somehow, it's as if there is no trade-off, okay? It's as if like what you want as a privacy person, which is not to leak too much about the training data set, it's exactly what you want as a learning person, because that is actually, like generalizability is an important property of machine learning. And like there is hope here that like you can use privacy techniques, but like even if you don't care about privacy, you want to use them because that's like good machine learning practice, okay? And you get better models that way. So there is no usual like trade-off in some of it. I mean, at the end of the day, you still have to deal with epsilons, and you still have to answer questions like, you know, so this epsilon of 5, like what exactly does that mean? But nevertheless, like somehow like here we're all in a happy place. So, so the hope here is to have something like privacy preserving machine learning, which has both good utility and good privacy and good generalizability, and kind of leaves us in a happy place. All right. So let me finish here, and I hope this motivates what Kobe has to say later. Thanks, guys.